So this is one of the method you can do that. But consider it's very difficult to maintain two wall with the same, without any expansion, without any displacement. So people may consider we don't need to count on the wall. We can work on the whole structure of the thermal actuator itself to make the displacement. So that's why people try to think of a different way. One way is by designing this, we call the hard arm and the cold arm actuator. The hard arm and the cold arm actuator actually is designed with one arm thinner than the other one. Okay, so this is a cross section. Okay, so the hard arm has a shorter, smaller diameter of the beam. Okay, but the cold arm has a large diameter of the beam. So when you flow the same current through this actuator, the hot arm can generate a lot more heat because the resistance is higher on the thinner arm. Okay, the thicker arm actually can dissipate more energy, and also the thermal energy is not generated that much. So we will get a higher temperature on the hot arm and a lower, cooler temperature on the cold arm. Okay, so end out, the hot arm will expand more than the cold arm. So end out will become like this kind of shape. It's kind of an arch shape. Okay, so on the hot arm, because extension is much more, it's thinner and extends much more. And the cold arm, we can think is another extension. There's no extension on the cold arm anymore. Anyway, so in this case, we can get a very large displacement here and bend up a little bit to form like an arch over here. So at the end of the structure, we can see the displacement, the deflection. So that's a displacement. For this, we call the hot arm and the cold arm actuator. So in this case, we don't need to fix two structure between two walls. Okay, if we do this, it's not easy to control. So we can expose all the actuator outside without the constraint inside two walls. Okay, so the car arm and two arm will finally form this kind of structure. Okay, so first we look into the resistance. The difference on the resistance is because for hot arm or cold arm, they have the same material property, resistivity though, and they have the same length, L. Okay, roughly the same. Okay, the same length. So the difference for these two arms will be the area, cross-section area. So remember, we have a hot arm thinner, smaller than the cold arm. Okay, so the cross-section area will be smaller. So when we plug into this equation, we can find out the final resistance of the hot arm will be higher than the cold arm. Oh, sorry, I think this is not correct. It should be reversed. It's resistance is proportional to the length, inverse proportional to the area. Sorry, I put this two wrong, two in different. Please correct it. Yeah, please revise, okay, your equation, the equation in your textbook. So resistance is proportional to length. Oh, sorry, not correct again. It's the surface area, okay. So resistance is proportional to length. Inverse is proportional to the area, okay, cross-section area, okay, of the resistance, okay. The equation here is wrong, okay. Please do some correction. Okay, so after understand this kind of situation, now we look into the final structure after you heat up the structure. So after you heat up the structure, you will find out some deflection at the end of the structure. So we will consider this kind of arch. So it's a part of a kind of a circle. It's part of a circle. So the circle, the radius of a circle will become r over here. And there is an angle from the beginning to the end will be theta over here. And the length of the cord, the core arm will be L. The hard arm will be extended much more. So the angle over here will be theta over 2. Okay, so this is a geometrical condition. So now we want to do the calculation about what kind of deflection this kind of actuator will have, and also what kind of force this kind of actuator can give you. Okay, these two questions. So now we do some calculation. So the length of the arch, okay, will be r times theta. The radius times the theta, the angle. Okay, so the length will become the hard arm's length after extension. Okay. And for the chord part, equal to L. Perform the geometry over here, the two triangle here. So the length here will be equal to R, the radial times the sine theta over 2. Okay. So this is half length of the total length. So times 2. So this will be the co-arm length. So hard length, the final length will be equal to R theta. The core length will become this equation. And so the total the extension, the thermal expansion of the hard arm will be the length of the arch minus the length of the chord. Okay, so it becomes R theta minus 2 times R sine theta over 2. The difference between the hard arm and the cold arm. Okay. And also we divide by L the length of the chord. Okay, the length of the chord can also be expressed by this one. So finally, delta L over L. That's a definition of our strength caused by thermal expansion. So this thermal expansion strength will be equal to alpha delta T. Depends on the temperature elevation. Okay, so now this equation is too complex. It's considered a lot of cosine and sine, the triangular function. So that's why we want to use in Taylor expansion to expand the equation to take only the first order of the first part of the equation to find out the theta, the angle will become square 24 alpha delta T. This is the results you got, okay, after Taylor expansion. So the deflection will be L times sine theta over 2. The deflection D will be at the end of the arm, okay? So the length of the deflection, the displacement of the deflection will be the total length times sine theta over 2, the angle over here. So that's a deflection. So you can plug in those equations over here. So finally, you can find out the original displacement delta L and the final deflection D. What kind of ratio you got? What kind of enlargement you have? Okay, so you divide this one by using delta L. You already developed earlier over here. Yeah, you can plug in over here. So in order, you find out it's about like 160 times enlargement on this kind of displacement. Originally, you have very small displacement. This kind of configuration, you can enlarge the displacement by 160 times. Okay. Yeah. So you elevate 100 degrees C, you can have a larger displacement. However, the force at the same time will be reduced actually, and you can plug in back the theta you calculate here, and to back to the equation and to find out the final force. Okay. Yeah. So there's a enlargement displacement by using the hard arm and the cold arm method. So there's one literature paper we put at the end of this lecture, so you can take a look later on. Okay, for the whole experimental results. Okay, so this is the first way you are doing this. The second way, we can consider another way by using a bimorph beam. So for the hot arm and the cold arm, the situation is you can extend the whole actuator outside, and there's no constraint on the outside of the extension. It's good. However, you have some kind of things happen. That means when you extend the hard arm, it's very difficult to design, actually. This portion, the flexible beam portion. When you extend the hard arm too much, the bending of the hard arm will be too much, and the flexible beam will define the deflection of the cold arm. So in this case, this part is very fragile. Not only it can be heated up too much, and also the structure-wise is very weak. So this kind of actuator easily to be broken at this position. It's not easy to design. And also there's some deviation between the position of the hard arm and the cold arm because of this separation of these two arms. There's only two connections, one on this end, the other one is on the electrodes. Only two connections over here. So basically they are separate to each other. So it's not easy, sometimes easy to operate, especially for upright positions. This can be used for the lateral driving actuation, but for the upright, up-down actuation is not easy, okay? So that's why people consider if we can combine two different materials together, okay? For example, like this, we combine two different materials together, okay? On the top and the bottom, we have two different materials. So when we heat up the material, so the composite material will be either bending up or bending down, okay? According to the thermal expansion coefficient difference between these two materials. For example, if you have aluminum on the top, consider the thermal coefficient, expansion coefficient of aluminum is larger, 10 times larger than silicon. So when you heat up the substrate, you can imagine the aluminum can extend 10 times more than silicon. So structure can easily bending down during the heating up process. So when you cool it down, you will bend over back, okay? So, so this kind of actuation we call the composite plate is we call it bimorph, okay? We put two different materials together with different thermal expansion coefficient. One is a larger one than the other, okay? So the situation becomes more complex compared to previous one. So you want to do some simple calculation about what kind of force and also how large a displacement this kind of actuator can give it to you. So first we can consider this kind of a composite plate. We want to give some assumption first in order to have a easier calculation. So we assume the structure looks like a plate, okay? It's two-dimensional. It's not a one-dimensional thing. It's two-dimensional things. It's like a plate. So the plate have three. Currently, we have two important dimensions, x and y. So on x and y, we can see the stress built up in these two directions. But on the z direction, there's no any stress because it's the surface on the top of a bottom surface. No stress built up on the surface. The stress is built up on the sides, not on the surface. Okay. And also, another thing you need to consider is we have an aluminum fin on the top, much thinner than the silicon. Okay, the assumption here is because we want to do some calculation later on. To simplify the calculation, we need to have some kind of assumption over here. But usually, when we put another material on top of silicon, the add-on material usually is thinner, actually. Okay, then silicon is quite, practical actually in real application. So the stress is biaxial stress. So when the structure start to bend, okay, the surface inside in each intersection will remain flat, okay, surface remain flat without a warp, okay, without a deformation. Okay, this is a basic assumption, okay. So from the equation of the Hooke's general law, so you will understand, okay, the strain, okay, total strain in some kind of direction will be caused by the stress from not only from its own direction, but also from the other two directions. For example, you have extension on x-axis. This stress will cause expansion on the x-axis, that's strength. But on the other two sides, you have a y direction and z direction also expand. But these two expand on y and z direction will give contraction to x-axis. And the ratio is we call the Poisson's ratio. It's not all, but partially affect the contraction on x direction. So this extension on its own x dimension, and they got a contraction, some Poisson effect from the other two axes. Okay, so the original equation. But here we consider on z direction we don't have any stress. Okay, because the surface. So when he got some stress, so it just expand. So it won't sustain any kind of stress on the z direction. It's freely expand. Okay, can freely expand. Okay, so we take out the sigma z from this equation. Okay, and also we have a biaxial strength, biaxial stress. That means sigma s equal to sigma y. Two axes they have the same strength. This condition. So in out we can find out the deformation, the strength in the x and the y axis will be the sigma x. Okay, because sigma x is equal to sigma y, so we're using only one sigma x times the modified Young's modulus. Okay, so the modified Young's modulus will be E over 1 minus Poisson ratio. So the modified Young's modulus will be a little bit larger than the original one. So when you want to bend the beam in only one direction, it's easy to bend. But you want to bend the beam in two directions at the same time, it's not that easy. It becomes harder. The Young's modulus become stronger, larger. Okay? Yeah. So in your practical thinking, usually you want to bend in one direction, it's easy to only make the curve in this direction. But you want to make two curves at the same time, it's not that easy, right? Okay? So from the equation, you can see the modification, modified Young's modulus will be higher, a little bit higher than the original Young's modulus. Consider Poisson ratio usually is 0.3 up to 0.5, depends on the material. So the Young's modulus, the modified Young's modulus is larger, okay? So after this understanding, now we go to the real calculation. So the case is very complex, so we draw very detailed figures here, and we will explain it later. So consider we have a bimorph beam. On the bottom, we have a silicon. Top, we have aluminum, okay? So when we heat up the whole structure, the aluminum part will expand, and the silicon substrate will expand not that much. So consider we draw a line, the center line. During the bending, actually, you can see the top part, because the aluminum film bend more. Silicon is not bending that much, so the whole structure will not stand too much. So the whole structure will bend down like this. Even though the silicon bend down like this, the top part of silicon will still expand. Okay. However, the bottom part of the silicon will be contract. Okay. So there will be a neutral surface. The neutral surface, that means on this surface, there's no any extension or contraction of the material. The material length keep the same at the neutral surface. 中心面，这样了解吗？中心面的那个位置，在中心面的位置的地方，这个材料没有伸张，也没有收缩，维持一定的长度。但中心面之上的这个部分呢，材料是伸张的；中心面之下，材料是收缩的。OK， 所以 silicon substrate 它的上面是伸张的，下面是收缩的。但是 aluminum film 伸张的更多。OK。所以但是它要跟 silicon 粘在一起，所以它必须被 silicon 拉回来。OK， 好，那 silicon 的话被除了它原来的伸张的量之后，还要被拉出去一些，所以变成这样弯曲的形状。OK， in Chinese it be easier to understand. So yeah, so because aluminum film extend much more than silicon substrate. So because they connect to each other, so the original extended aluminum film need to be contracted back by the silicon substrate because it is connected to the silicon substrate. And in silicon substrate, after thermal expansion, you need to expand much more, a little bit more, to accommodate, connect with the aluminum film. So that's the final result you can see. In order to accommodate this kind of situation, so the whole structure will be bending down like this kind of structure. So above the neutral surface, this part, the materials are expanding, but in different degree. When you're close to the neutral surface, the expansion or contraction is not that much. But when you are away from the neutral surface, there will be more expanding. Okay, more expanding. So like the curve I draw here. So the distance from this curve to the boundary will be the extension degree of the material on this position. For example, on the fin, aluminum fin, will expand that much more. The expansion of the aluminum fin will be that much more. For silicon, on the border will be this much. And when they are close to the neutral surface, the expansion will become smaller and smaller. So the relationship is a linear relationship. Okay? So larger and becomes smaller. And on the bottom, the silicon original position will be here, and they feel the contraction. So the distance here, from here to here, becomes shorter than the neutral surface. So on the bottom, these are the length of this the bottom of the material will be the shortest one. Okay, of all the silicon substrate. So it contracts the most. So on the top extend the most, on the bottom contract most. Okay. Okay. Now we stop here, have a break, and we will continue later. Okay. Thank you.